Welcome back everyone, this is lecture 29 and we are getting close to the end of our Quantum Field Theory 1 course, right? So what we want to do for these last two videos is to go over a few processes in QED, right? Because they will serve as examples of full calculations that you can do in quantum field theory that are actually directly comparable with experiments, and also serve as a testing ground to see if you really understood the whole method of calculating these things, right? We will also learn a few tricks as we go through these examples, especially how to deal with Dirac matrices. So we want to start with non-relativistic processes. And in fact, the very first one I'll do is not even QED, it's just for the Yukawa interactions, but then that easily becomes something that you can do in QED, right? And the idea here is to look at the non-relativistic limit of quantum field theories, where we can compare these scatterings we can do in quantum field theory with the scatterings you can do in quantum mechanics, right? In the non-relativistic limit, this theory should reproduce known results for quantum mechanics scatterings, right? And in that case, we could, in principle, look at what potential. Remember, scatterings, in one way of looking at scatterings in quantum field theory is in quantum mechanics is to look at the scattering by potential, right? You just put one particle being scattered by external potential. Right? So you could ask, suppose I take the non-relativistic limit of this quantum field theory, it should be equivalent to some potential, right? And we'll look what potential that is for two interactions, the Yukawa interaction and of course QED, right? We should expect that in the case of QED, we will recover the Coulomb potential if we're talking about point charges. So let's do that. Let's take a look first at the Yukawa interaction. The interaction I have in mind is this one, right? In Minkowski space, it's just a G, so coupling G, psi bar, psi, phi, right? And I could even imagine there's more than one fermion in my theory, so that could be something like that, right? Many fermions, right, interacting through the same kind of interactions. The same scalar here. So this fermion phi 1 could exchange a scalar with this fermion phi 2, right? And the couplings could be different too, right? I don't care about these details, right? Let's assume they are equal for now, right? We know that the Feynman rule for the vertex that arises from this kind of interaction is something like this, right? So you have three interaction with three fields and two fermions and one scalar, and that in Minkowski space leads to this rule, just minus z times the coupling. So now the process I have in mind is one fermion is scattering another fermion by the exchange of this scalar, right? In the case where these fermions are indistinguishable, right? Suppose they are the same fermion. I have two diagrams, which I'll draw here now. So there's one fermion scattering another one. And let me label everything here. So this guy is incoming with momentum k, spin r. This one is outgoing with momentum k prime, spin r prime. This one is incoming with momentum p, spin s. And this one is outgoing with momentum p prime, spin s prime, right? I also want to label the vertices because I want to keep track of the spinor indexes. So I assign an alpha to this vertex and a beta to this one, right? And also they exchange some momenta on the scalar line here. And I'll call this momentum Q oriented in this direction, right? This is arbitrary, right? But with this orientation, I know that Q, by momentum conservation, Q is just P minus P prime, or K prime minus K. If these fermions are indistinguishable, then there is another diagram, right? Let me copy this. Right? Because I can exchange these final Fermion lines, right? I can come here and do, let me move Q to the side. I could do this assignment here. I'm still keeping the upper one as K prime, momentum K prime, and spin R prime. The bottom one still has P prime and S prime as momentum and spin. But now see, the fermion that has momentum K prime is coming from the bottom vertex, this vertex, and not that one. And that changes momentum conservation, right? So Q now is P minus K prime, or P prime minus K. I have a different result. But this is only if they are indistinguishable. Otherwise, if I can put a name to these fermions at the final state, then I can say I'm calling momentum P prime the momentum of this particular fermion and not that one, right? So those only contribute if they are distinguishable. Now let's write the Feynman rule for these two diagrams, right? So IM is, I have twice the vertex, right? So it's minus IG square. Now I just have to follow the Fermion lines. Let's follow this one first, right? This is a U bar of S prime P prime with spinor index beta. This one is U of S P, again index beta. Let's write the propagator for the scalar, right? It's I Q square, right? But Q square is P minus P prime square. And the mass, I'm calling the mass of the scalar M phi, right? So it has mass M phi square. And the other Fermion line is just U bar of R prime K prime with index alpha times U R of K with index alpha, right? This second diagram, right, it's different from that one by the exchange of a fermion, right? I'm exchanging this leg by this leg. And we know that when that happens, there's a relative minus sign, right? The coupling is the same, minus IG square. And now I just have to follow the Fermion lines like I did for this one. So I start with a U bar of S prime P prime. Now the index is alpha, right? And a U of RK, index alpha. You see how the contractions changed. The scalar propagator will also be Q square minus M phi square, M phi square, but now Q square is different. So this is P minus K prime square minus M phi square. Right? And then the other Fermion line, right, it's just U bar starting from here, U bar R prime K prime index beta contracted with U of S P index beta, right? And those are the two contributions to this process. Now, I want to make a few considerations, right? The first one is that since I'll try to compare this with quantum mechanical scattering, right? I want one of these guys to be a scattering center, right? It's just one of these two fermions, the only role it will play will be that of generating a potential, and the other one will be scattering in that potential, right? Remember, there's no potentials in quantum field theory per se, right? This is a non-observable quantity. But I want to compare that with quantum mechanics, right? I want to see what would be the potential in a quantum mechanical calculation, right? So it's much better, in order to do that, to consider that one of these fermions is much heavier than the other, right? Because then it's basically not moving there, and the lighter one just comes and scatters off of it. So I will take one of these guys to be much heavier, so they will be distinguishable. So I don't need these two diagrams. I did both because the objective here is to do example calculations, right? And that's the whole calculation. But in fact, I will only use this first line, which is the first diagram. The second thing is that I'll take the non-relativistic limit, which allows me to simplify the kinematics here a lot, right? So let's see. The first thing is, since the energy is low, right, I can write all four momenta in the following way. I can take the energy to be basically the rest mass of the particle, and then I have three momenta here, right? And I will do that for every one of these for momentum. So P prime, same for K, and same for K prime. And that allows me also to simplify these expressions, right? For instance, this P, I will only use this first line, and this P minus P prime here, square. In the case where the energy is just a mass, right, I'm left with just the three momenta squared, right? The difference of three momenta squared, because the energy part is just m minus m, right? It's just 0. Also, U can be simplified. I know that in the non-relativistic limit, US of P is already given by square root of m times the spinors, the spin direction, right? Which I'll take in this basis, which is the simplest one. And that allows me to simplify these products of U's, right? So U bar S prime P prime times US of P can be simply written as U dagger of S prime gamma 0 US, right? And that's, I get a square root of m from here and a square root of m from there, so it's just m psi of S prime dagger, psi of S prime dagger, times the gamma 0 matrix, which in our convention is 0, 1, 1, 0. And here I have this psi of S, psi of S, psi of S. Right? This is easy enough to multiply, and I get 2m, and I'm calling m now the mass of the fermion, the lightest fermion. I won't need the mass of the heavier one, right? So in this case, I even put them the same, but I must be careful with that. In principle, they are distinguishable and they have different masses, right? But the lightest one is easy enough to write, and I have these psi prime dagger, psi s, and this we know is the Kronecker delta of s prime. Right? This allows me to simplify this line. Let me copy it. Now they are distinguishable. I only really need this. And in the non-relativistic limit, this is just, let me get all factors of I and G here, will be IG square over vector P minus vector P prime square plus M phi square, right? I'm using this approximation right here, so there was an extra sign, and I hope all signs are properly taken care of. And for this and this expression, I'll use what I have here, right? Is just 2m delta s prime s and 2m delta r prime r. The first nice thing we learn here is that on this low energy limit, right, this non-relativistic limit, the spins of these two fermions will not flip. Whatever was the initial spin will be the same for both fermions, right? So I can mostly forget the dynamics of spin, right? And now I want to compare this with a result from quantum mechanics, right? What I want to imagine is a situation where one of these fermions, and I'll take the fermion with momentum p to be that one. So it started as I was drawing here, right? One of these guys started with momentum p and finished with momentum p prime. I'm not talking about spin anymore, right? So I'm looking at the momenta only now. And this guy is scattering out of some external potential, right? So there is now a target here, right? And there is some interaction between them. We know that's the exchange of scalar excitations, but this guy is scattering from external potential now, right? And since I don't want to care about the dynamics of this guy, I will assume that the momentum transfer is small compared to the momentum of this guy, and then I can forget about it. In practice, that implies that the energy is conserved, so the module of the momentum is conserved, but the three momentum changes, right? Now I'm thinking of a one-to-one scattering, right? I'm not looking at this guy anymore. So this part I don't care about anymore, right? And my matrix element now will be that of a one-to-one scattering, which will be equal to IM, this IM, right, 2 pi conservation of energy only, EP prime minus EP, right? Another way of thinking about this is this, right? Normally, my previous diagram was this one. And this is equal to 2 pi to the fourth conservation of momenta, right? All momenta, sum over all p's and k's, right? And times the rest, I mean, the expression for the invariant matrix element, right? Now, since I'm not observing, I'm saying the momenta of this guy basically does not change because it's too heavy, right? So I have to integrate over this. So the integral over the momenta of the target, since I'm not observing it, right, is of the same diagram is 2 pi delta energy. Only the conservation of energy is left, right, times the rest of it, right? And this is what I'm writing here, right? Becomes a one-to-one scattering because I integrate over the momentum of the target, and that eliminates 3 of these deltas and leave me just with that. So that's the expression I'm going to use, right? So I can plug this IM here, remember, without this part, because this is also part of the dynamics of the target, right? I can plug plug this here, right? And I want to compare with some result from quantum mechanics. So my first approximation is now to assume that the transfer momentum is small compared with the momentum of the target, right? And now from the side of quantum mechanics, one approximation that I can use, which I'm actually already using in this calculation too, is that the scattering potential is weak, in the sense that I can use the Born approximation to calculate the transition amplitude, right? We know from quantum mechanics that the transition amplitude of a scattering from a potential, it is, again, a one-to-one scattering amplitude, right? Is given by minus I V of Q, where Q is the transfer momentum, 2 pi delta of energy conservation. And you see it's very similar to the expression we have above. Right? This is the Born approximation, and Q is the transfer momentum, is just Q, is just, in this case, is the change here, right? It's P prime minus P. Right, so this Born approximation is valid if V is weak. I mean, it's a weak potential, and otherwise I would have higher powers in V, right? But that approximation is consistent with the perturbative expansion I'm making here. I'm taking the basically one insertion of the interaction here too, right? So these two expressions are actually very similar, right? And comparing both, then I get that my potential, right? I just have to compare both. I'll get that V of Q is given by minus M, right? Which is written up here, right? The one detail I have to be careful with is that in here, I'm using a relativistic normalization, and that's why I have this 2m factor here. Also, I'm not looking at spins, so I'm assuming the initial and final spins are just the same. So this is 1, right? And this 2m here is from my relativistic normalization of the states. This does not appear here because in quantum mechanics we usually use a different normalization. So I have to either ignore this 2m here or put a 2m right here, right, using a different normalization in quantum mechanics, right? In any way, I get to the same relation, right, which is important to see, and without this 2m. So the potential is just V of Q equal to minus G squared Q square plus M phi square, right? That comes from here, right? The I goes away because I have an I here, an I there, and this is pretty much what I wanted, right? Still in momentum space. What we really want to know is the potential in position space, right? So we have to take the Fourier transform of that one, d3q, right, of minus G square Q square plus M phi square exponential of I Q X, right? I'll spare you the details of these calculations, but if you're curious, that's on my lecture notes page 201, right? And the answer is this: V of X minus G square over 2 pi over R, right? R here is the module of X, so it's really the distance, right, to the center of the potential, exponential of minus M phi R, right, which is the famous Yukawa potential, right? So we can learn a few things here. The first one is the heaviest this scalar particle that is being exchanged between the fermions, the faster this potential will go to zero, right? It is exponentially suppressed in comparison with a similar Yukawa potential, right? And the heavier the mass of the scalar, the shorter will be the range of this interaction, right? So that's the first thing we learn. In fact, that's the fact that Yukawa used to estimate the mass of the pions, right? Back when he proposed this process to explain why nucleons were bound together inside a nucleus, right? He used like 1 Fermi as the effective distance here, and that led to a mass of a few hundred MV, right, for the pions, right? And the second fact we notice here is that this is an attractive potential, right? Here we must be careful because this expression right here can be a bit misleading, right? It seems like I'm tying the sign of the potential to the sign of the matrix element. But we know that this is an amplitude, right? So this is defined minus constant, right? I could change the sign of the M, and it might look just superficially that might change also the sign of the potential, right? This is one of the few instances where I have to be careful about the overall sign of M. So in regards to that, it pays to be careful, right? The first thing to notice is when I used my Feynman rules up here, without saying, I was careful with that, right? I know that there was, just by looking at this exchange of final fermions, you can see that there is a relative sign between them, right? But I also put the right overall sign for this guy by doing, and you can do that pretty easily, the following analysis, right? If you look at the diagram there, I had something like P prime, K prime, psi bar psi acting on point X. I'm looking only at the fermionic part. And psi bar psi acting on Y, and then P, K, right? Using the conventions we are using, right? This can be written as 0, A K prime, and A P prime, and this is the convention, right? And not putting A here, right? This is the same, but let me write it like this. Y, and then on this side, this is the convention. Right? And the convention is actually chosen on this side, right? And on this one, it's the opposite because they need to be the Hermitian conjugate, right? If I decide to write PK, PK must be the Hermitian conjugate of PK. So that's the convention we're using, right? So these are fixed, right? And this will be important. Let me keep it here. So if you look at what kind of contraction I need to make here to get my diagram, right, the diagram I want to get is this one, right? Where P and P prime meet at one point, right? Let's call that point Y. And K and K prime meet at another point that we can call X, right? Let's call this point X and this one Y. Right? And let's go back down there. Now, what contractions do I need to make here? Well, it helps to first bring this guy over here, and that's 2 commutations, so it's a total sign plus, right? And then I copy this with this guy over here. And then there's no more signs, right? I said that P prime and P meet a point Y, and that's the contraction that does that. And the other 2 meet at point X, and that's the contraction that does that, right? So the total sign for this diagram is a plus, right? And that's why in my expression, I didn't put any sign for the first diagram, and I put a minus on the second. Usually you don't have to pay attention to this, right? You could put a minus on the first diagram and a plus on the second, which would not be totally right according to your conventions, but that wouldn't change the modulus of m squared, which is okay. But in this calculation, we need to know m, and that demands that I do this analysis. But you could think, what if I change my convention, right? What if my convention was this instead of the previous one? That's a minus sign in comparison to what I had before, right? I exchange these 2 operators that anti-commute with each other, right? The problem is if I do this here, right? In order to keep the opposite side, the Hermitian conjugate, right? I also need to change my convention to the other side, right? So I cannot just change one side, I have to change both. And you can see if I change one sign here and one sign there, nothing will change in total. In fact, I can now do this, right? I can bring this guy over here, and then the contractions would look, right? The x's now are on the edges. This is a plus, right? It will be the same as taking this thing here and doing the opposite, right? Put x, y, y, x. Now with the A and A daggers exchanged. And you see the total sign is still a plus, right? Which is, I got a minus from exchanging here and a minus from exchanging it over there, right? So that is fine, right? What I'm saying is that my change of convention for these 2 fermion state will not change the overall sign of this matrix element. But you could ask further, right? More in general, right? I could change this matrix element by a complex phase, right? I could just change the normalization, this state, by a complex phase, right? And have an extra complex phase here, which again could be turned into a sign, right? But in this case, you have to be careful because I'm using one transition amplitude and comparing with another transition amplitude. And while the absolute phase of this state, which appears in both, and this state, which appears in both, right, is not significant, the difference is, right? This potential is causing a shift in the phase of the state that is being scattered, right? We know that from scattering theory, right? So if I change it here, I also have to change it here by the same amount, right? This is more clear in this case where I don't have K anymore. But even if I had K, a change in the phase of the target, right, I also would have to appear here, but in a less obvious way. I mean, I would have to change this expression by the same phase. But in any case, this relation stands, and the sign of the potential is uniquely determined, right? If you change the phase on this expression, you need to do exactly the same change of phase of convention in here, right? In order, and that's what keeps the sign of the potential significant, right? So we are getting an attractive potential, and that's a physical statement. So what happens if now I do the exact same calculation, but instead of using this Yukawa interaction, I use QED. So I'm talking about doing again a Fermion scattering. So my IM will be still a scattering between two fermions. I'll keep almost all conventions the same here as far as possible. Right? So my momentum is K, R, K prime, R prime, P, S, P prime, S prime. But now, instead of exchanging a scalar here, I have a photon. Right? And that means that these vertices are not Yukawa vertices anymore. They are QED vertices, so now they have more indexes associated with them, right? One Lorentz index and two spinor indexes, which I was called gamma delta. Right? And in this case, I have called this mu, and the spinor index will be alpha and beta, right? But Q, the momentum of the photon is still called Q, and it is oriented in the same way the scalar was before, right? And this is the expression for Q, right? And I'm not even drawing the second diagram because I know that I will make these two guys have different masses, so they are distinguishable, right? So if I write the Feynman rules in the case of QED for this, right? That's pretty easy. Let me start with the bottom Fermion line. This is very similar to the one with the Yukawa, but now I have more indexes, right? So that's S prime, P prime with index alpha, right? And I have a gamma matrix here, which I'll write, right? This is just the coupling of QED, right? But I have gamma mu alpha beta, which are the spinor indexes, right? USP, which is this line, right? Beta. Now the propagator for the photon, I'll take the simplest gauge, right? Which is the propagator is just G mu over P minus P prime square, which is Q square, right? So minus I G mu over Q square. And then I have the other Fermion line, which is U bar R prime, K prime, gamma, because I choose these indexes, the QED vertex, mu, and notice that this is wrong. This should be nu, right? So the indexes of the gamma matrices are contracted with the photon that is going between these two vertices. So nu is contracted here, nu is contracted there, and I have U, R, K, and I forgot the indexes here, should be gamma, delta, delta for the spinors, right? Now I have to take the non-relativistic limit again, right? Very, very little changes because I have this gamma in the middle, but if you look at it, right, this is U bar S prime, P prime, gamma 0, USP, which again, if I use the non-relativistic limit for these guys, right, that will be M psi S prime dagger, psi of S prime dagger, gamma 0, I have an extra gamma 0 here, right, which is there now, psi S psi S, right? Which is, in this case, this is just gamma 0 square is 2m delta S prime S, right? So at least for the index 0 here, nothing changes. What about the gamma I, right? The other three components for this gamma in the middle here, right? In this case, what I have is U bar S prime, P prime, gamma I, get some more space, USP, right? Again, I have to use the non-relativistic limit for these guys. It's just M psi S prime dagger, psi S prime dagger, right? And then if I use the conventions for gamma I in the representation I choose for the gamma matrices and multiply it by gamma 0, what will appear here is 0 Pauli matrix sigma I minus sigma I, 0, right? Psi of S, psi of S, right? And this minus sign here guarantees that this is 0, right? Because I have the same expression twice with a minus sign between them. So really only gamma 0 contributes. Notice that this is summed over all gammas, right? Because it's summed with this G mu here. Same here, but only the zero, the zero component of this contributes, and it contributes just like before. So on that front, I have a very similar result, right? This will be IM will be. Now let me collect all factors of I. Let me quickly remove me from the picture there, right? I will collect all factors of I. Please check. Right? Should be minus I E squared. Of course, G00, because as I said, this is summed all over, but only gamma 0 will contribute on both sides, right? Over P minus P prime minus P squared. And again, in the non-relativistic limit, only the vector part survives down here. That means there was an extra sign in front of this, right? Contributing to this sign here, right? And for the rest, I just have the same as before, 2m to S prime S and 2m S R prime R. Right? This guy is 1, right? This is just 1 in my metric, right? So that's basically the result we got for IM, right? And then we could go through the whole logic that we went before, but it's all the same, right? I can straight away just write V of Q as minus M, forgetting all these relativistic normalizations, forgetting spins. It's basically just minus these without the I. So V is now E squared over Q squared, positive, right? So because I invert this sign. So that's important. Let me box it, right? And this is the momentum space potential, right? It's very similar to the one that I got from the Yukawa one, right? The two differences are the coupling is E instead of G, but that's just a name I gave to the coupling, right? I have Q squared here, but here I have this mass. In here, I don't have the mass, which indicates it's what we will expect because the particle you're exchanging now has 0 mass, right? And most importantly, the sign is the opposite, right? Which indicates that we will have a repulsive potential. In fact, if you take the Fourier transform of this, you get a very well-known potential, right? Which is just E squared over 4 pi r, which is the Coulomb potential, right? In fact, we used to rename this E squared over 4 pi as alpha. It's a very important constant. It's the real coupling constant of QED, right? So this defines this guy, and that's my Coulomb potential, right? Repulsive, right? As you would expect from two fermions, right? These are two particles, so they have the same charge, right? Which begs the question, can I see that if I exchange one of these particles by its antiparticle, would that become attractive? Let's start answering this by the Yukawa interaction, right? So what I'm talking about is, suppose we take that diagram we already calculated and do this, right? So now I change one of my two fermions, it doesn't really matter which one, right, by an anti-fermion, right? So now I have an anti-fermion going through that line. In terms of the Feynman rules, what changes is that before I had for that line U bar r prime, k prime, right, u r of k, right? That was the rule before. Now it becomes a v bar r k, right? Because now I have an outgoing anti-fermion and an ingoing anti-fermion, which is given by v r prime k prime. Right? So that's the main difference in terms of that line only, right? And now on the non-relativistic limit, this is given by m, right? Nothing changes here, psi dagger of r, minus, so this minus is important, right? Because the v is psi minus psi dagger of r, right? In here I have the same, so this is just gamma 0, right? And in here I have psi r prime, and again minus psi of r prime, right? And that means these two signs here means I have an overall total sign, minus 2m delta of r prime, right? So it might look like I just got a change in the sign of m and thus the potential, right? But that's not all. Let's keep in mind there is this minus sign here, but also now I am exchanging, right? Where before p, k was given by a dagger of p, a dagger of k, acting on 0, now this guy has become a b dagger, right? And that means that while before, and I want to compare these two, right, I had something like that, right? 0, a k prime, a p prime, psi bar psi at some point, let's call this x, right? Psi bar psi at some other points, let's call this y, right? A dagger of p, a dagger of k, right? And you had some contraction which was needed here. So p must meet p prime at this point y, right? And k must meet k prime at this point x. Now, when you exchange some of these guys by b's, right? So now k is an antiparticle with momentum k, so it's b. And here, the same thing, is b, right? It just so happens that psi bar does not contract with b, only with b dagger. So I need to exchange these lines up here, right? So This guy will now contract with B dagger, right? And this guy will contract with B, because remember, it matters if it's B or A, because one of these guys contains A and B dagger and the other one contains the opposite combination. The question is that now that I exchange A for B's, I have to exchange these contractions. And just by looking at these two, you see there's a minus sign between them. I have to, in order to get the same number of commutations I have here and here, I have to exchange these two guys, right? Right here. So I got a minus sign here, but another minus sign here in order to get the same diagram. So the total sign remains the same. So for the Yukawa, so what we learn here is that for the Yukawa interaction, it does not matter if I'm scattering fermions with fermions or fermions with anti-fermions. The potential is always attractive, right? This interaction is always attractive. I didn't show this last one, antiparticle and antiparticle, but you can imagine it is the same, right? I'll get, when I do change this line for an antiparticle, right? I'll again exchange the U's that I have here for V's, right? I'll get a sign here, but again, when I change this A, and this other A for B's, again, I have to get an extra sign here, because now I'll contract this guy to the right and this guy to the left, right? So it's also true that if I do antiparticle, I will still keep the same sign, because I have this cancellation with the sign that comes from changing U into V's, right? With this sign that comes from the different commutation, right? So as far as the Yukawa interaction is concerned, it is always attractive. What about the Coulomb one, right? Well, this discussion remains the same, right? I don't care if this is a Yukawa interaction or a QED interaction, right? The QED would have some gamma matrices here, right, and here. But these gamma matrices are in spinor space, right? I can just write everything here explicitly with the indexes of spinor, right? And then I can put the gamma matrices aside, even outside this bracket, right? And the logic of how many times I need to commute these anti-commuting operators will be the same. So in QED, I get a sign from this rearrangement of the contractions if I exchange a particle for an antiparticle. The question now is, do I get a sign also for exchanging U's into V's? Right? Let's look at that. Right? So in the case of QED, I had U bar S prime P prime gamma 0, U S P, which in the non-relativistic limit was 2m delta S prime S, right? Which now will change into V bar of S prime P prime gamma 0 V of S P. Actually, yeah, the primes go over here, which is given by M psi of S dagger minus psi of S dagger, gamma 0, right? Now I have two gamma zeros because of that, right? Psi of S prime, psi of S prime, right? Minus psi of S prime. But now this is the identity. That means that this sign, remember the difference comes because when you exchange U by V, you get a sign here. Since this is the opposite diagonal here, this sign multiplies this guy and this multiplies this, and I have a total sign. Now, instead of the opposite diagonal, I have the identity between them. That means this sign meets that sign, and I have exactly the same result as before. right? That sign does not matter now, right? The sign here, because they are multiplying each other, right? Which means I have no change of sign when I go from U to V, right? I get the same expression. Since I do have a change of sign here, that means that for the Coulomb potential, it will become attractive. It was repulsive before, and now it will become attractive. And of course, if I go and change again, go to the other particle, right? In this case, I did the change with the one with momentum P, but suppose I then go and do the same with the one with momentum K, then I change the sign again, because nothing changes here. It changes in the contractions, and it becomes repulsive again. So like charges repulse each other and opposite charges attract each other, which is a relief to have, right? We wouldn't believe this theory if it gave anything different from that, right? So hooray for quantum field theory now. Another really interesting result from quantum mechanics that we can easily get here is the one of Rutherford scattering, right? Which was basically the scattering of somewhat light charged particles by very heavy atomic nuclei, right? So these light charges were scattering out of the Coulomb field generated by these heavy nuclei that you again are not recoiling, right? So they are static, right? We can reproduce that, and it's interesting to do that because we can also see how to mix fields which we are quantizing with classical fields, because in this case I don't want to worry about individual photon exchanges between the nuclei and the incoming charged particle, let's say an electron now, right? I want to treat this electromagnetic field as a classical object. So the interaction I will use, right, the interaction Hamiltonian, will be this one, which is the usual thing for QED, right? This is my interaction, right? But when I go and calculate the scattering of fermions, I will again do a one-to-one scattering, right? Because again, the dynamics of the nucleus does not interest me, right? And also, I'm not interested about individual photons, right? I know that this scattering is done by low energy photons, right? Which is what you had in quantum mechanics, right? So this guy I can rewrite in this way. dt, right, where hi is the one above. And to first order in perturbation theory, the first term that will contribute to scattering, right, if I assume P is different than P prime, is this. Time ordered minus I d for x psi bar E gamma mu psi a mu, psi a mu P, right? And the contraction that will help me here is this one. But notice that A, right, is not the operator here, right? It is a classical field. You can think of it as the A classical that we defined before, right? Because in terms of photons, I have vacuum here and vacuum here for the photons, right? There's no photons here, no photons there. So if this was an operator, the result would be zero, because the annihilation operator for photons would hit the vacuum on the right side, and this would be zero. So this is a classical object. I'm not doing a path integral over it. It's just a function that is there, right? And that's the way we treat classical fields interacting, I mean, with quantum fields in scattering, right? So this then is equal to minus IE, right? Just gathering all factors here. When you contract this guy, you get a U bar of P prime. I'm again ignoring spins, right? But let's say there's a spin S prime associated with P prime and a spin S associated with P, right? Gamma mu U of P, right? That comes from this contraction, right? And I end up with D for X exponential of minus IPX, again from this contraction, and exponential of I P prime X from this contraction, right? The contraction gives me the exponential times one of these two functions here. And you have A mu, which is a function of X. So in the end, right, this is to order E, right? So the first order in the interaction. This is just minus IE U bar P prime gamma mu U of P A mu P prime minus P. Notice the similarity with this equation. In fact, as an exercise, you'll be able to prove something very similar. Where is it? To the Born approximation here, right? Using a similar idea where the classical object is this potential, right? So you see, you can obtain that, right? So now if I assume that this electric field generated by the nucleus, right, is independent of time, so if A mu of X does not depend on time, then you can say that this is the Fourier, this guy is actually the Fourier transform of this one, right? So if this guy does not depend on time, that means that this guy can be written. So this is actually just a function of X. That means that guy can be written as A mu of P prime, vector P prime, vector P times the Dirac delta in energy, right? Because it's a constant in time when I do the Fourier transform, right? So if this potential is actually not varying in time, that means the momentum space potential has a conservation of energy, right? And then I can rewrite again this object as, let me substitute this here, minus EIE U bar P prime gamma mu U P A mu of P prime minus P times 2 pi delta of EI minus EF, right? Which now is really, really similar to the expression we had for the Born approximation. In fact, if we make all the same considerations for a one-to-one scattering, right, we concluded that a one-to-one scattering should be IM times 2 pi, just the conservation of energy, because the conservation of momentum goes away because I'm not considering this scattering, the nuclei, right? The nucleus in this case, right? I'm not considering the momentum of the nucleus. Very similar to what we just did, right? And in this case, I have a new Feynman rule, right? Everything up here. Let me just reorder this. Take this I put here, put the minus here. All of this is M, right? Let me color the whole thing. This is M, which allows me to read a Fermion rule for these external fields, which we use quite frequently, right? If you take a look at this, you see that the Fermion rule for this external field is just this part here, and we usually indicate external fields like that, right? And again, since this is a QED vertex, right, I have index mu, I also have indexes alpha and beta from the spinor indexes contracted here, but I will not repeat them. The important thing is that I have an index mu that needs to be contracted with a mu there, and I have some momenta that is going through here, and this I can write as minus I e gamma mu a mu of q, right? Which in the case we just did, right, q is just the change in momenta for the charged particle that's being scattered. So it's just p prime minus p, right? So this is the rule for external field. It contracts, it's the rule for the whole thing, right? The vertex and the Fermion and the classical field here, right? The only other rules here is the rules for the external fermions, right? Now I want to use this expression here in a cross-section, right? But it is a one-to-one cross-section, which we didn't derive before, right? The idea I have right now is let's make this definite. So let's take an electron, right? And let me put the original trajectory here as a dashed line. And this guy is scattered out by some nucleus that will be characterized by the atomic number Z here, some distance away. And I can define, if I take this original line and take the plane orthogonal to the direction the electron was going, I can define an impact parameter which will be important, right, as we know. Now we calculated the phase space for 2-to-2 scatterings and 1-to-n in case of decays, but we didn't calculate 1-to-1, and that's what we want to do right now, right? So my differential probability in this case, of course, depends on that impact parameter, but also on a transition amplitude of 1-to-1, which is given by this. So for any particular final angle of the electron, PF here, right, I can have this differential probability. And this is the relativistic normalization we have been using, and this is the transition amplitude for final momentum PF and for an initial wave packet, which I'll call phi A in. Right? This wave packet will, as usual, right, as we did before, be characterized by some normalizations times the integral in the initial momentum, right, of some phi of ki times eigenstates of momentum, right? And this is what gives the shape of this wave packet, right? This function can be chosen as to give different wave packets, right? Using this, we can do the usual game of writing the differential cross-section, which will be given by an integral over all impact parameters of this expression that depends on B. I can even put a B here, which is, now let me write this explicitly, d2b, and then I'm putting this guy in. As for this part, I have to take care in consideration this times pf phi a star, right? So I'll do an expansion in k for this guy and an expansion in k bar, right? I use the variable of integration for this part as k bar, right? Like we did in the 2 to 2 case. So that gives me two integrals like that, d3ki and then d3ki bar that I'll write later, right? And now I'll put all the proper normalizations here. So there's a 2 pi cube, there's the wave packet, wave function there, again more normalizations, right? Now for this part I have d3ki bar phi star, this ki bar over the same normalizations, square root of 2a ei bar, right? Also I extract from these wave functions an impact parameter, right? So I have something like this here, right? This is just a complex phase that I can take out of the wave function to take care of this distance, right? Since I have that for both, I end up with e exponential of I b ki minus ki bar vector, right? And all that is multiplying these, substituting this wave packet by the momentum state, right? So I get out state with momentum pf times ki in times out pf bracket with ki bar in. So that's the thing I need to calculate, right? Now we know the game here. There is a lot of Dirac deltas everywhere, right? So just to start, I won't do this calculation in details, but I want to indicate what you need to do, right? This guy is just Im times 2 pi conservation of energy. Again, same logic. I only get conservation of energy here because only the module of the momentum is being conserved. Remember, there's an external source of the field that is acting on this guy. So the momenta is transferred to that external source, and essentially I'm not keeping track of that momentum. Right, this other guy is very similar. Actually, I forgot a star here, right? It's the complex conjugate. I just have to take this, take the complex conjugate. So there's a minus here, and put star here, and put bar everywhere. So this is ki bar, this is ei bar, right? And there's also another, two more Dirac deltas coming from the integration on the impact parameter, right? I can do the integral in B, d2b of that exponential I b ki vector ki bar vector is just 2 pi square delta of the perpendicular ki's, because B is in that direction, right? So what I call ki perpendicular minus ki bar perpendicular, which makes already two of the components of the momenta, of the initial momenta, I mean this ki and the ki bar, the same. right? Now I can combine all these deltas, right, and start eliminating this bar variable. Eventually I can get rid of the bar variable and contract this phi with that phi to get a module of phi squared, right? And then there's more deltas because I can assume that this is narrow, and the best way to write a narrow wave packet is to just use a Dirac delta with the proper normalization. So for this initial momenta, right? Once I use enough of these deltas to prove that Ki bar is just Ki, then I get phi square here. And that allows me to use choose a shape for my wave packet, which then allows me to eliminate the integrals in Ki, right, that I didn't yet. Right? Same game as in the 222 scattering. If you're curious about the details on how to use these deltas, it is on my lecture notes, page 204. Take a look there, but it is simpler than the 222. The final result will be, I'll write it straight out here, that the differential cross section divided by the solid angle, right, which is part of the integral in P, right? The solid angle came from this D3 momentum here, D3PF, the final momentum. I separated in the integral over the module of this momentum and the angular part. And the angular part is this d omega that is here, right? 1/16 pi square. All these factors come from using all these deltas. VI, EI. I here means initial, right? So this is the initial speed and the initial energy of the electron. And this is the integral over the module of the momenta. So PF now is just the module of the initial, of the final momenta, right? And there's a conservation of this module, which came from one of these conservations of energy there, and the matrix element square, which we know, right? This is the matrix element that I have in yellow up here, right? So that's it. Now let's actually implement this idea. Now I'm specialized the scattering for an electron and a nucleus, right? So let me copy just the expression for the matrix element, right? So this is what I want to calculate. Let me put it here. And if it is just a nucleus sitting there and not moving at all, I know how to write the electric potential, right? A0 of x for just a nucleus will be z times the charge, right? Divided by 4 pi r, right? Which means that in momentum space, I just have to do the Fourier transform of that. A0 of q will be z e over q squared. Right? So that's the field I put here, which means that, and all the other components are 0, right? And so out of this sum over mu here, only the 0 term contributes, and I can write m as minus E U bar PF. I was calling the final momenta P prime and P. I'll just change to the same language I usually use in phase space, so I'm calling this PF now, right? Gamma 0 U pi, right, times this guy. Yeah, times this guy. Which I can rewrite more conveniently as minus ZE square U bar PF comma 0 U pi over PF minus pi square, right? So that's what I want to plug in the cross-section formula. But I can simplify it a little bit further, because we can take the non-relativistic limit here, right? Remember, we're trying to reproduce Rutherford scattering, and the formula that Rutherford got was for non-relativistic electrons. So in that case, this piece we know how to calculate. We did it a number of times already in this video, right? This is just 2m delta of S prime, or S and S prime are the spins of these guys. I have not been carrying the index, but I know they are there, right? And that means that if I calculate m square, now this will be using this formula, right? Z square e to the fourth, right? And then I have this twice, because I'll take the square of this. This will be 4m square delta S prime delta S prime S over this guy to the fourth. Right? So this is what I want to plug in the cross section. Even more, I want to take, I'm not worrying about the spin of the electron. So as usual, I have to sum over S and S prime and take the average over the initial spin. So there's a factor half. Of course, this is really simple in this case, because this, right, I can use one delta to make the sum on the other. And when I do the sum on the second delta, will be a delta SS, there will be 2. So this is just 1. I just eliminate that from there, right? So if I don't care about the spin, I just take these spins away and I'm averaging over them. I get this expression without the deltas. So the sum over S prime of modulus of m square is this. Take this out, move these guys here, right? The expression gets simpler and simpler, right? And I can also simplify this thing on the bottom, because remember, I have in the cross section, now this is the expression for this outside the cross section, but I know I'll plug that in here, right? And I have this delta, which forces the module of these two momenta to be the same, right? And that means that PF, let me write a proper PF minus PI, right, which is usually 2, let me write like that, square root of PF square plus PI square minus 2PI PF cosine of the angle between them, right? It's just now I can take these two guys to be the same, right? And just substitute everything for PI. So it'll be PI square, and another PI square here. So I can take a PI square outside. And in fact, there is 2pi squared here and 2pi squared here. So take an extra power of 2 outside the integral, outside the square root, right? And leave 1 over minus cosine over 2, which is just the sine of theta over 2, right? And that's what I get here, right? In the non-relativistic limit, I can write this momenta as just 2 times the mass VI sine of theta over 2. Now finally I'll plug it in the cross-section formula. Let me copy it. Right here, right? And write everything again. The sigma, the omega is over 1 over 16 pi square. I'll just copy this part. This integral is just done using this delta, right? So PF will be in fact PI, and PI I use the non-relativistic approximation, which is just m times the speed, the initial speed, right? And then I copy this formula down here, right? It's just m squared, and I exchange this part by this to the fourth, right? Now I have to do a lot of cancellations here. Also, I use here the non-relativistic approximation, so the energy here is just the mass. That means that this goes away with this, right? This is just the mass of the particle, right? And I write in here, I use my definition for alpha, right? Alpha is e squared over 4 pi, so I can take this e to the fourth and turn into alpha squared, just absorb the proper powers of pi and 2 from here, right? So this becomes z squared alpha squared over 4. Again, some powers of 2 went in here, right? 4 m squared vi to the fourth, and the famous sine fourth of theta over 2, which is the Rutherford formula, right? Obtained through quantum mechanics, right? Now we did it using quantum field theory, which is another reality check. It's always nice when you're dealing with some new theory to take limits of it that fall back to a theory you already know. So we have shown at least 3 important checks, right? We got the Yukawa potential, we got the Coulomb potential, including testing if these potentials are attractive or repulsive between particle-particle, particle-antiparticle, etc. Right? And now we see that the Rutherford scattering formula can be obtained too. In this case, it's already a mixed calculation, right? We're using the quantum excitations of the electron of a fermionic field to represent the electron, right? But the nucleus in its electric field is represented through a classical field, right? Because I'm looking at a soft scattering, right? I'm not exchanging high energy photons, which would have to be represented properly by excitations of the electromagnetic field, right? In this case, I'm thinking about a classical field, and you see how that works and how we can obtain results from that. But now, enough of this non-relativistic nonsense, right? The reason I'm studying a relativistic quantum field theory and going through all this work is because I want to look at events that cannot be treated properly in quantum mechanics, right? So let's do that. Let's look at intrinsically relativistic scattering. which is the unpolarized scattering of a pair of electron-positrons. So I have antiparticles here, right, annihilating or scattering to go into some final state, which I call L bar. L here means lepton, and our first thing will be to understand physically what I'm talking about. So leptons are like a category of particle that includes the electron, the muon, the tau. These are all negative particles, but also the neutrinos, the neutrino of the electron, the neutrino of the muon, and the neutrino of the taus. These are all called leptons, and the reason they are called leptons is because of their interactions. Specifically, they don't have color interaction. Otherwise, they will, if they interacted through the exchange of gluons, they would be quarks, right? So none of these guys has any color interaction. And L bar here just means the anti-lepton. So for all these guys, each of these guys has some antiparticle, which in this case, for these guys, just the positive, and for the neutrinos, I indicate like that, right? And so these are the leptons, and the phenomena I'm trying to describe here is what happens when I throw an electron against a positron, right? Which is an experiment that was done, in fact, right? There was some very important electron-positron accelerators that did measure this, right? And I have many cases here. Lepton here means any of these guys, right? And since we're talking about QED, already I know I'm not talking about the neutrinos. The neutrinos have zero charge. So if I want to have neutrinos here at the end, I need some interaction that the neutrinos actually feel. Otherwise, I will not produce them. And they do not interact with the electromagnetic field, right? Because they have no charge. So all that is left is these guys, right? The charged lepton, right? The first case is when this is actually the electron again, right? So then I'm talking about E minus, E plus, right? Going to E minus, E plus, right? In this particular case, there's two diagrams that contribute, right? Let me put them here. Right? Either I could have the electron and the positron annihilating and producing photon, right? That then decays and produce a pair of electron-positron, right? Or I could just have the scattering of an electron exchanging some energy and some momentum with the positron, right? Remember, time is going to the right here in my convention, right? These two cases are undistinguishable because in any case I have an electron and a positron at the start and an electron and a positron at the end. So these two diagrams will interfere with each other. You could have, if you wanted to look at this, you would have to worry about relative signs and all that. In the case of the muon and the tau, remember that the other two charged leptons in my list here are the muon and the tau, right? In that case, then I don't have this second diagram because the electron cannot just become the muon by emitting a photon, right? In the case where I get E minus, E plus going into mu minus, mu plus, right? Only this diagram contributes because this I can do, right? I can think of an electron annihilating a positron. That vertex exists, right, in nature, and then this photon decays into mu minus, mu plus, right? Of course, if you don't know anything about the standard model, you could think, what about this vertex, right? E minus, mu plus, right? And well, that vertex just does not exist in the standard model, right? I can give you some intuition, right? These guys are not particle and antiparticle, and they have very different masses, in fact. But yeah, the point is that this vertex is not in the standard model, right? And these are. So this is a possible event, right? And the same for the tau. If I put the tau here, it's exactly the same diagram. In fact, the only difference as far as this production is concerned, right? The only difference between the muon and the tau is the mass. The tau is much heavier, right? So I propose we calculate this using the muon. Of course, for the tau, you also have the result. You just exchange, in the final answer, you just exchange the mass of the muon by the mass of the tau. Let me already choose my conventions here for all the momenta. So I'll call the momentum of the electron P, the momentum of the positron P prime. I'll orient this momentum Q in this direction, and I'll call this again K. I'll call this one K prime, right? And with these conventions, Q is P plus P prime, or equivalently K plus K prime, right? Everyone is oriented to the right. And notice here all particles are distinguishable, right? Each of them has characteristics that I can use to distinguish, right? So electron and the muon have different masses, the electron and the positron have different charges, the same between the muon and the anti-muon, right? So everyone is distinguishable here, right? I can know a little bit about thinking only on kinematics, right? I can know which of these leptons is possible in the final state, right? It's easy to understand that if I want to create some leptons here at the end, the total energy of the electron, say in the center of mass, right? If I go to the center of mass of this initial electron-positron pair, right? I need a center of mass. Right? I need that energy to be bigger or equal in the limiting case, right? To 2 times the rest mass of these final states, right? Otherwise, I don't have enough energy to produce them, right? This is always true for the electron itself, because at the very least, the energy, if I put the electron and the positron just sitting there close to each other, right? The center of mass energy will be twice the mass of the electron. So this is always true for the electron. So I have a few possibilities, and I'm ignoring quarks here, right? I'm thinking only about leptons, because I could also produce quarks here. Quarks have charge, so I can use electron-positron to produce quarks, right? But thinking only of leptons, right? If the center of mass of energy is smaller than twice the mass of the muon, the only possible final state is this, right? If this center of mass energy is between twice the mass of the muon and twice the mass of the tau, then I can produce this final state and also this final state, mu minus mu plus, right? And in this case, there's a probability to produce E minus E plus and a probability of E plus and minus. I have to calculate these 2 cross sections, right? So there will be, this is random, right? This is a probability distribution that I can calculate here, right? And if the center of mass energy is bigger than twice the mass of the tau, then I can also produce tau. And again, I have a game that even if at these higher energies, I can also produce electrons, right? And I have to calculate the relative probabilities here if I want to, right? But let's calculate the muon production, right? Mu minus mu plus. So let me just copy this because I won't have too much space here. And I'll write the Feynman rules for this, right? Differently from the case where I was calculating a potential, now I don't have to care at all about the absolute sign of this. So I won't be doing that analysis of how many contractions I need to do. I'll just straight out write the Feynman rule. Let me start with the line of the electron here, right? Since I'm starting with a positron, right, I get a V bar S prime P prime. So I didn't write here, but I'll use a spin index S prime for the positron and S for the electron, right? There's a electromagnetic vertex here, which is minus I E gamma mu, right? And then the U S of P for the electron, right? Remember, I'm suppressing it here. I'll bring it back when I need it, but there are spinor indexes which are contracted here, right? So this is a matrix product between these three guys, right? This guy is a vector line down, and right, a line. This is a column, and there's a matrix in the middle here. Then I have the propagator for the photon, which again I'll use in the gauge, which is simpler, is minus I g mu over q squared. I could put a I epsilon here, right? But if you do momentum conservation here, you see that this q squared cannot be zero. So I'm not on the pole. I don't need to carry this, right? I can just keep this q squared there. And then there's the line of the muon, right? Which is, again, I'm starting here from a muon going out, so it's mu u bar r. I'm using r for the spin of the muon. K, again, the electromagnetic vertex that needs to be contracted. So remember, I'm not doing that again, but maybe I should. I'm putting an index mu here and mu there, right? So this is gamma mu. The photon propagator is g mu, and this is gamma nu, right? And I forgot the electric charge. And this is V r prime, k prime for this antiparticle going out, right? By the way, I didn't say, but I'm doing these diagrams at the first order in QED in which this scattering is possible, which is using two vertices. So this is proportional to E squared on the amplitude, right? There is no order E diagram that you can draw that does this, right? Of course, there are bigger next to leading order terms. This is the leading order one, is when the scattering becomes possible, right? Notice again that the indexes for spinors are contracted here and here, so I could in principle take this whole block and put to the left of these or these, right? But inside those blocks, if I want to commute this guy with this gamma or this V, then I need to put the indexes explicitly. Then I can commute anything, right? But so far I'm keeping these blocks together, right? Let me do a little bit of simplification on all of that, right? Take all powers of I here. There's minus I here, minus I here, minus I there, right? That gives me a plus I E square for these two E's. This q square I'll bring to the front, right? And then I have these blocks which are matrix products in spinor space, right? And I'll keep them encapsulated for now because I don't want to write all indexes straight away. S of P, right? And I can take this g mu here, right? And just bring this nu down as a mu. So that becomes u bar r K gamma nu, right? V r prime K prime. So this object behaves as a Lorentz vector, and it is contract with this other Lorentz vector right here, right? So far so good. Now I want to calculate the module of m squared, right? And in order to do that, I need to calculate m complex conjugate of m. In order to do that, it's important to notice a few things. So take an object like this, v bar gamma nu u, right? And let's take the complex conjugate of that, because when I'm taking the complex conjugate of m, I'll have to do that to these two guys, right? As I said, all the spinor indexes here are contracted. So if I put some spinor indexes explicitly here, you'll see they are all contracted, which means this is a number, right? This is not a matrix in spinor space, right? And that allows me to write these colors, right? To write this as the dagger, right? And the complex conjugate is the same as the dagger for a number. But the dagger is much easier to apply inside. So now let me take the dagger of all of this, right? Remember that this guy is just V dagger gamma 0, right? So this becomes U dagger gamma mu dagger, right? Gamma 0 dagger V, right? V dagger dagger, which is V. We know in our convention that gamma 0 is equal to gamma 0 dagger, so I can eliminate the dagger there. And we also know that gamma mu dagger, gamma 0 is gamma mu. If you don't remember this, go back to where I first defined the Dirac matrices. This is true in our convention. Right? That means that I can multiply by gamma 0 from the right here, actually from the left here. And using that gamma 0 is 1, gamma 0 square is 1, right? Write this. So when I commute a gamma 0 with gamma mu dagger, I remove the dagger from gamma mu, right? Which allows me to write this as U dagger gamma 0 gamma mu V, right? Which is just U bar gamma mu V, right? So when I take the complex conjugate of objects like this, and I use V and U here, but I could have used U and U, U and V, V and V, it's all the same, right? I don't use any special properties of U or V, right? So when I take the complex conjugate of an object like that, right, with gamma nu in the middle, right, I just exchange these two guys here, right? And I can use that straight away there, right? And that's pretty easy. So I can write, with that in mind, I can write these matrix element squares straight away. So m squared will be just, in here I'll get a minus I multiplying this I, so the I goes away, e to the fourth, q to the fourth, right? And then these objects. Let me copy these two. Let me make them smaller so they fit on the screen, right? Is this readable? Yeah. Right. And of course, now when I take the dagger of these guys, I just have to exchange them. So I'll have V bar r prime k prime gamma mu u of rk, well, which is the complex conjugate of this one, right? I have a lot of hidden indexes for the matrix multiplication there, but I don't care about those. And now I have the complex conjugate of that one, which will be USP bar gamma mu V S prime P prime, which is quite nice. So I found my matrix element square. Well, let me check real quick. I think everything's fine. So now, remember at the title for the video, for this part of the video, I had unpolarized scattering, right? And unpolarized means that the initial electrons are not polarized, and also I don't care about the polarization of the muons that I produce at the end, right? We know what to do with that, right? I need to take sums over spins. So I have to, for each of these spin indexes here, S prime, S, R, and R prime, right? I'll have to put a sum, right? And then use these two important properties, right? If I pair US of P, which is here, with US bar of P, which is there, right? And now I have to be careful with the indexes, because this guy will have some spinor index I, this guy will have another spin index J, right? And this will be P slash plus M. And then I have to look at this momenta, right? Is this the mass of the electron or the muon? Depends on what momenta is here. In this case, P is the mass of the electron, right? And these guys will carry an index, right? So this will be the IJ component, right? In this case of the identity, but in this case, there's a Dirac matrix there. And I have a similar expression for V, right? If I take here V and V bar, there'll be a minus right here. And again, the mass depends on which moment I take, right? And in this case of the V here, it could be an electron. For this case, it could be a muon in this case, right? So that's what I will use. But in order to do that, right, when I do all these sums, and of course, in the end, I take the average over the two initial spins. So I'll multiply everything by a factor 1/4, right? In order to really do these pairs and find these relations, now it's really interesting to actually explicitly show the spinor indexes. So let me copy this thing down here. And let me name all these indexes the same way I did in my notes. So I'll call this I, J, J, right? K, which is bad notation, but anyway, K, L for this Dirac matrix L. This guy I'll call M, M, N, N, and this one will be O, O, P, P, right? And now I have pairs, right? I have to find these pairs with the same spin and always the same momenta too, right? And let me indicate those pairs here. So this guy, when I do the sum on R prime, will be paired with this one. This will be paired with that, right? This one will be paired with that one, and this last one will be paired with that, right? So now let me write all of this, right? So now I'm talking about not about m squared anymore, but 1/4 of the sum over S prime, R and R prime of M squared. And this is equal, right, to e to the fourth over 4q to the fourth, right, this 4 right here, right? Let me copy all the gamma matrices. All the Dirac matrices go right there. Also, I need to be careful here to change, right? These guys were contracted. So mu was contracted with mu here, and same for nu over there, right? I forgot this, so I have to be careful. So gamma nu Mn, gamma nu OP, right? And now I have to write all these contractions, right? Let's start from this in the middle here, right? This is just, so K prime slash, right? Since it's a V, it's a minus M, and K is the momentum of a muon. So this is the mass of the muon right here. And the indexes are LM. Right? Next one is again K. This was K prime. I have to be careful for the slash to not cover the prime. So this is K slash. Again, now this is a nu, so it's plus the mass, but the mass is again the mass of a muon. And the indexes are NK, right? Notice the ordering, right? The bar needs to be to the right of the one without the bar when you look at the orderings for the indexes. Right? Next one is now a P slash, right? Plus M, but in this case is the mass of an electron, because this is the momentum of an electron, right? And the indexes are JO, right? JO. And the last one is P prime slash, right? It's a V, so minus M, and electron, right? This is an electron, and the indexes are PI, right? Now, I have to look at this carefully, right? And identify the matrix contractions, right? I want to get rid of all these green spinor indexes, right? And that's easy enough to do. Let me do that real quick. Spin of M squared is equal to this part I just copy, right? And take a look at gamma mu. Gamma mu KL, then goes here LM, right? Then goes over here MN, then goes here NK, right? Which goes back to the initial gamma mu KL, right? So I got a trace, I got a cyclic thing here, and just looking at those indexes, I know the order. This will be a gamma mu, right? K slash prime minus M mu, gamma nu, K slash plus M nu. So this is a trace for the muon line, right? And I got another trace. I just have to follow this gamma nu here, right? And close, you see that that closes another trace for the electron line. So gamma mu P slash plus M E, right? Mass of the electron, gamma nu P slash prime minus M E. Now, the next step would be to learn, let me box this, it's very important result, right? But the next thing it would be to replace this inside the cross-section formula, right, for a 2-to-2 scattering. But those traces seem like something impossible to integrate. Remember, I'll have to integrate over these momenta that are inside those traces, right? So what we're missing here is a whole technology that we know on how to calculate the traces of Dirac matrices, right? And that, so we'll stop this calculation for a second to develop this technology. But this video is getting too long, and so we'll continue with that on the next one. See you then.